Recording's rolling. It's Tuesday, January 13th. So, where's your paper? Where's your notes? Guys, everybody pick up your notes. So, remember yesterday I took you guys most of the way through Unit 5 on AP Classroom. There were just a few puzzles left, and I want to move on with other things. So, um, yesterday I made a separate video. It's only about 10 or 11 minutes long to explain a lot of it that I didn't quite get to yesterday. And that's uploaded to Google Classroom. So, like, especially if you weren't sure how to solve those, and just check that out. It's like pork and principles. All right, so we're going to move on to angular momentum and rotational kinetic energy, right, which my AP's book is Unit 6. Oh, I did not make a note on here to look at AP Classroom Unit 6, but you guys know that that's open, and you need to debrief that with you guys pretty soon, next few days. Right? So, so you guys know AP Classroom Unit 6 is going to be the material that we covered today. I'm going to show you guys some demos, and then bring out the posters and explain how this works. Rotational dynamics quiz, you guys know I'll get to you guys next week. You guys know that there's no school Monday for Martin Luther King Day, and then sometime next week. And for AP, I'm going to split it into 2 days. So day 1 is going to be the material we covered so far. Day 2 is going to be the content that I'll cover start today. Another note here is there going to be school pictures next Friday, so Friday the 23rd. Senior panoramic. So if you're a senior, they're going to call you guys out first period and do a panoramic. If you're in a school club photos are going to be throughout the day. So you can get that information from your clubs. All right. So that's what's going on there. All right. Wait, what? Actually, here. Let's do gyroscope. Gyroscope. All right. All right. So I did. Have you guys ever spun a gyroscope? Right. No. Or you've probably spun a top though, right? It's the same principle, the same idea. What you guys are about to see, or if you spin a coin, didn't I flick a coin and it was spinning on its side the other day? You guys remember that? Right. No, I've got this video muted, but just so you can see what this does. Right. So if you spin a coin or spin a top, in this case a gyroscope, it'll stay upright. It won't actually fall over. Why is that? Well, until maybe some frictional force, right? If it's not spinning fast enough, it'll eventually fall over, right? So you can do something like that with it. If it's spinning, you see it's processing around. What's that about? Can you balance it on a string? Yeah. All right. So, what's the physics principle going there? All right. So, in a nutshell, it's called conservation of angular momentum. So, you guys remember regular momentum? Linear momentum was mass times velocity. Okay. So, in place of mass, we're going to have rotational inertia. Okay. So something to do with this looks like maybe a cylinder spinning, right? And then in place of linear velocity, we'll have angular velocity. Okay, so the fact that this does have to be spinning, rotating, so in radians per second, right? Right, and it wants to maintain that value. Now, guys, do you think angular momentum is going to be a scalar or a vector value? What do you think? Right, remember, what makes a vector is that what matters? Direction. You guys, the fact that this wants to maintain its orientation is maybe a hint. This has to be a what kind of vector? Has to be a vector. Yeah, vector. Right. So yeah, it wants to maintain that orientation. Right. Now, why is that? I think last semester I was recommending to you guys to watch a Vsauce video called Spinning. I think I've uploaded this link a couple of times to Classroom already. You guys remember this? Right, Spinning. Right. Hopefully you guys have watched this already. Now I'm just gonna point a couple of parts here.
In the direction of my force. Pretty simple. But if the ball is moving before I touch it, its velocity doesn't just disappear. Instead, both combine and the ball moves according to their sum.
Right, now that's just regular linear momentum, right? But he's about to turn this into rotation.
The lower its initial momentum, the greater this angle. Now, let's go back to circular motion. Imagine a satellite orbiting Earth. Its velocity is, as we showed before, at all times tangent to its circular path. A centripetal force from gravity continuously swings its velocity around so that every 90 degrees, it starts pointing more and more in the opposite direction it used to be. Just like with the ball, a downwards force won't send it straight down. Instead, the vectors combine, resulting in a new path like this. 90 degrees ahead, it reaches the maximum distance it will travel in the direction.
All right, so that's the key right here, right? What he's right in the middle saying, right, is that if say the satellite's going around a circular motion, right? Say on that green ring, right? And he pushes down on it right here, like a downward force, like bam. Right? Notice that this orbit doesn't shift down. It doesn't reach its maximal down direction at the point where he applied the force. Okay. So if you think about this as like a point mass, right? The lowest part of its new orbit, which is this blue orbit, is now going to be 90 degrees ahead in its motion. Guess that from where he applied that force? Guess that? Right?
Direction of our force before going back. The key point here is that a downwards force at this location didn't move the orbit like this. It moved the orbit like this, tilting it 90 degrees ahead of where we acted.
Right. Okay, now what if that wasn't a single satellite? What if that was like a trillion satellites and they were all connected in a ring? Right? They would all be like doing the same thing as a single point mass, but now you have an aggregate effect.
Now, imagine the satellite
There
as
you
a
go.
small piece of our gyroscope. Pushing down here will cause the piece to assume a path that would take it like this. But of course, since the disk is solid and all of its pieces quite rigidly push and pull each other, the gyroscope itself tilts like this. Or if the gyro pivots around a point below its center, like this. If the gyro wasn't spinning, pushing it down here would have just caused this to happen. But when something is spinning, its component parts have other vectors you need to consider. I learned a fun demonstration of this from a great video.
Okay.
Felt 90 degrees.
My work is easy because I use Click.
Okay, well,
Here's how I keep track.
guess that means we're done. Right, so when the gyroscope say starts to lean a certain way, oops, right, back over here. Right, actually, do I have a gyroscope? Here we go. That's right here. Right, say when the gyroscope is going to lean, say this way. Now, if it's not spinning, of course, it'll fall that way. Okay. But if this thing was spinning, and there's a little hole here, you can put a thread through and then pull it, a little string, okay, to get it spinning real fast. Okay. Okay. Then say if it's spinning counterclockwise like that, okay, then it actually wants to lean this way, right? And then it'll start to precess and it'll go around like that. Are you guys seeing something like that? Here's my spinning point. Here, show you guys. Right. See like that. Okay, there's a little bit of precession that's going on. All right. So let's look at the poster version of these. You guys know, of course, I've been teaching this class many years, so every classic question I see show up year over year over year just turns to a poster. So these are going to be the questions you're going to get on the AP exam or some kind of connection. Okay. And so there's a really classic setup, and I've mentioned this setup a few times already. So if you have this turntable, right, this turntable right here, and you wrap a string around it and you pull the strings. Okay. Now, conveniently, as you're pulling the string, this string tension is always perpendicular to this radial arm, isn't it? Always perpendicular. Okay. So he's getting assigned at 90 degrees. So this cross product, you just multiply the values. Okay. What's this radius times this force? Okay, so we got a circle. Okay. You guys, if there is a net force, say like this tension, okay, now you have a torque, and because you have a torque, you have an angular acceleration. So this R cross F becomes I times alpha. You guys see that? Okay. Now, really, that's strictly only true if there's no friction with the axle, but that's a common simplification. They might say there's no friction at this axle point. Okay. Of course, you want there to be friction between the string and the disc, but not with the axle. Okay. Something like that. So you pull this. Sure. Okay. 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 You guys go with this? Because this could be really, really handy. Yeah. Okay. With a number of these rotational dynamics puzzles. Okay. But something else is happening too, which is that this disc, of course, has some rotational inertia. Okay. Which means that as you're pulling it, isn't it going to be spinning faster, faster, faster? Okay. And how fast is spinning? Well, that's what this angular velocity is. Okay. Okay. Which I guess would be increasing if you're applying a continuous torque here. Okay. Okay. But that's going to give it this angular momentum. Okay. So now we're back to this gyroscope. That could look a lot like that, couldn't it? Something like that. Right. And you know what I have too is now this doesn't show up super well on camera, but maybe in class. I have this bicycle wheel. We got a bicycle wheel. Okay. Now, if you get this bicycle wheel to spin, what I'll be able to do is to just balance it on my finger right here. This an axle goes through the center. Okay, it's gonna look like it's levitating. All right, so this is just for you guys in class. Okay. So now if I just try to hold it right here, it's just gonna fall straight down, right? Okay. But if you give this a spin, okay, so it looks like it's like levitating. But notice it's also processing around at the same time. Okay. And what if I hold it on the other side? Does it process around the other way? Yeah, it's processed around the other way. Okay. Looks like it's like levitating there because it wants to maintain its orientation. Speaking of one, maintain its orientation. If I try to turn it, it really resists change in motion. So I can really, it feels like there's a force against me as I'm trying to turn it. Okay. If I was standing on a turntable, actually, I have a turntable. Right. Right. So I'm going to be the only one standing on this turntable who can do this. What do you think is going to happen if I stand on the turntable while I do this? It's going to move.
Oh.
It's going to turn me around like that. Yeah. All right. Actually, you know what? Let me go back to that. That was another part I wanted to. All right. Let's get past buying whatever we're supposed to buy here. All right. Actually, there was. Here we go. Here we go. Actually, I can kind of show you guys what I was doing.
Like this. This force at its maximum impact 90 degrees ahead in the rotation, so the wheel will turn like this, but, well, there's still a torque here pushing the bottom of the wheel this way, moving that 90 degrees ahead, we see that the wheel will just keep turning, and in fact, that's what it will do. If I can get it up to a fast enough speed, then, ta-da!
Alright, so that's pretty much what you guys just saw, right? Alright. Okay. Now we got angular momentum going on. Alright. Now angular momentum. Right, here you go. Here it is properly. Angular momentum is I times omega. Now we talked about earlier, this is a vector. So oftentimes you'll see a little arrow above the L. Right, and sometimes I'll draw that too. Little arrow here. Did I do on the agenda today? I think I may have. Yeah, so you put a little arrow above that L, right, to indicate it's a vector. Okay. Guys, what about this omega? Angular velocity, is that also a vector? So I could put a little arrow above the omega also, if you want to. Yeah. What about rotational inertia? What do you guys think? Is that a vector or scalar? Yeah, that'd be a scalar. Right, that'd be a scalar. All right. Now this is something that wants to be conserved. Right? That's what you guys saw in those demos, say with the gyroscope and whatnot. Where did I put did I lose the gyroscope? Up here. All right. So guys, when you guys watch figure skating in the Olympics coming up pretty soon, right? Say there's a ice skater that goes into a slow rotation, and they bring their arms in, right? Now, when they had their arms out, right, their mass was distributed far away from the axis of rotation. It kind of reminds me of something like this, doesn't it? Right. So what if you go from where your mass is like spread out to where your mass is closer in? Right? You actually can see if you compare these two. It's kind of going from this picture to this picture. Right? What happens to the rotational inertia from left to right? Yeah, it decreases, right? Actually, so this is half of this, isn't it? Something like that. Yeah. Some of them are square decreases. Okay. Right. But if the angular momentum is conserved, then your velocity has to increase. Okay. Now, you guys, I know I've shown this Paul Hewitt demo already, but it never made it to the official recording on Classroom yet, so you guys get to see this again. I mean, it's worth seeing again anyway, right?
Oh, that's you guys.
Do I have this? I muted this. Here.
So if I get here rotating like this and I hold them out, what happens when I pull them in? Ooh, easier to rotate, gang. Harder to rotate, easier to rotate.
Yeah. Another classic question that's related to that is, did you guys see a question recently that had to do with like a giant nebula in space, big old space dust? Right. If it gravitationally attracts, what happens to the rotational inertia? Well, rotational inertia.
It was shrink.
Yeah, it would decrease, right? Decrease. Right. But angular momentum is going to be conserved. That's what this says. Sum of angular momentum before and after the same. Okay. So guess what happens to its rate of rotation? Its angular velocity would also increase. Just like you guys saw with Paul Hewitt. I got that. Right, now, here, go back to this picture. Right, so this here. What if you made a graph of, say, torque versus time and angular momentum versus time? What would that look like? Okay. Here, and I've got these side by side. Okay, so here's torque versus time. Guys, what if you're playing a constant force here? Do you guys see that? Constant force? And this radial size is also constant. Well, if that's constant, couldn't torque be constant? And torque versus time could look like this. Do you guys see that? Okay. Now, I want you guys to predict over here. I have another graph, and I'm covering it up right here, covering up this other graph. Angular momentum as a function of time. Let's say it's the same story. What do you think that graph knows like? Guys, make a prediction in your notes. Big prediction. What do you think angular momentum versus time looks like? Oh, by the way, AP will ask you this question on the exam, so score at least 1 point on your AP exam right here. I don't know exactly how they're going to ask it. Might be multiple choice, might be free response, might be some variation on this. It might have a variable torque maybe. Right? But some version of this is going to show up.
But it's probably gonna be.
Okay. Well, say.
That's gonna be linear.
Maybe you have to know what's the relationship between torque and angular momentum. Okay. So here, let's do. Here, what could be really helpful is this right here. Guys, this right here. Okay. So I'm looking at the AP equations. It says angular momentum, change in angular momentum is torque times time interval. Okay. So here, write that. Change in angular momentum is equal to torque times time interval. Right? Do you guys see how that's analogous to something we did last semester? Do you guys remember impulse, like change in momentum? What was that? What's the analogous formula from last semester? Okay, yeah, mass times velocity, but you could also say you get it from what times what? Yeah, force times time. You guys remember if you apply a force for some time interval? That could also be mass times change in velocity. You guys remember that? This is called impulse. Okay. Well, here's the rotational version of that. Okay. So, okay. And here's a graph I'm showing, say, a constant torque for. Okay. No, there is a passage of time. Okay. Okay. Okay, so put it all together. If I have a constant torque, that means some property of L versus T is going to be constant. What property do you think? The slope. Aha. How many guys drew that in your notes? Drew that. There you go. Okay. So these two graphs are related. Okay. So if you have a constant torque, then angular momentum versus time is increasing at a constant rate, so that would be a constant slope. Okay. So the slope of this line is the coordinate of this curve. Okay. Yes, I do. Okay. Now, guys, what about this? What if I went back to this turntable and I applied a non-constant torque? Like, what if I'm pulling with a greater and greater tension? Okay. So I start off with a small tension. Tension grows bigger, bigger, bigger. So this line right here was at an angle. Okay. If that was true, what would this graph on the right look like? A parabola. It sure would be. It'd be a parabola. Okay. Okay. Ooh, here's a fun one.
Oh, I did know.
Right, so spinning a basketball. How fast the basketball goes spin? So I'm gonna put the basketball on my finger. I'm gonna give it a little take.
Sure, letters, and then just
Okay, some force at this radial distance. Okay. And how fast is it gonna spin? Right. Well, guys, the fact that it's a basketball, isn't its mass all on the surface of a sphere? Pretty much. Right. Would that be different? A different outcome than if it was like a solid foam ball? And I give it the same force, right? Yeah, it would spin differently. So that's gonna go. Right, so let's apply this right here. This is that equation straight off the AP page I just showed you guys. It's right here. Angular momentum, the accumulation of angular momentum could be torque times time. Right, that's that right there, isn't it? Right. Hey guys, here, let's go step by step. What do you think? Are you guys okay with that so far? That's straight off the AP equation page. Okay, we're gonna make a series of substitutions. And the last step is going to say omega equals something. You guys see that? Omega equals something. Okay. 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 Let's see if you guys can predict. Next step, all the way down. Okay. What do you think I'm going to substitute for torque? What do you think goes right there? R cross F. Aha. Yeah. You guys at the radius of the basketball, I applied some force. Pow. By the way, what type of force would that be? It's like it's not a tension. It's a what? It's not a weight. I'm going to hit that with my hand. Pow. How about a friction force?
it is friction.
I think that would be a friction force. Okay. Yeah. How about or probably mostly friction. Right, and then time interval is sleep there. Oh, whoops. Okay. Ask you guys, what do you think you're going to substitute for angular momentum? I times omega. Okay, I times omega. Is that true?
No,
Okay.
which then we're going to.
Now, I okay, this I right here, they would have to give you, right? Like you would not be expected to memorize this expression. Let's say I give you this expression. So for a spherical shell, it's called basketball spherical shell, 2/3 m r squared. Okay, I is 2/3 m r squared. Like so you would have to know how to substitute that if that was given to you. Okay. So that goes right here. Okay. Now I think it would be reasonable if they gave you all these values at this point. Like if they gave you the radius of the basketball, say mass of the basketball, the applied force, and also the time interval of the applied force. Like, did you apply the force for like a half a second? That could go in for delta t. Okay. So, isn't there enough lying around you can solve for this omega? Just do a little algebra rearrangement. Okay. Now, guys, there's going to be a partial cancellation. What variable partially cancels?
R.
Yeah, the r. Can you get rid of it over here and get rid of the square over here? Okay. So it's still part of the end result, right? But there's a little. Right. So. It would be that for the basketball. And I put the 3/2 in orange because that's specific to the basketball. That comes from the rotational inertia of the basketball. Now, guys, if they said a solid foam ball, how would that change? Suppose the ball was made out of solid foam. Which rotational inertia do you think you're going to use? Yeah, solid sphere. Right. And that could be this right here, 2/5 m r squared. Okay, got that. Okay. And then this would be your 2 or 5. So how would the end result change? 5/2. Yeah. Okay. How about this? What if I had this going on? Okay. Have this. What if I really simplify this, guys? What if I simplify this to the point that I call it basically a solid cylinder? I mean, okay. Could you use this instead? This 1/2 right here. This would be 1/2. This would be 2/1. Right. So depending on what shape you're trying to rotate. Right. Okay, you guys good so far? All right, this one here, guys. AP asks this question every single year, so look for this one. These two discs, and okay, so I just picked a classic situation that they could probably ask. There are always variations on these questions, though. Okay, but what about this? What if you have one disc down here, this green disc, and it's already rotating with some angular velocity? It's already rotating. Okay, it also has some rotational inertia. We're going to take another disc, let's say this is not rotating at all, and I'm going to slowly lower it. That's these arrows right here. I'm going to slowly lower it until it lands on this disc. Let's say there's also some friction between the two, so they stick together. You guys see all that? Okay. And I'll tell you something about their rotational inertias. You guys see here it's like a 2-to-1 ratio rotational inertia. You can make up numbers if you want to. Now, once they stick together, do you think that the green disc, however fast it was spinning, is going to overall slow down? Yeah, right. And this gold disc that's landing on top, well, it used to not be spinning at all, but it's going to stick with this one, so it's going to definitely speed up spinning. Right. But guess what the guiding principle here is? In terms of angular momentum, what happens to the overall angular momentum of the two disc system? Conserved. Aha, conserved. Okay. So now we're going to do this. We're going to make graphs. So guys, in your notes, do this. Do angular momentum as a function of time. So I'm covering up as a function of time over here. Angular momentum is a function of time. Okay. And starting out, the okay. Here, put a notch down here for this gold disc. It's not spinning off. Guys, it's not spinning at all. It doesn't have 0 angular momentum. 0 I times omega. Okay. I got a couple of lines up here. I got a green line starting because this green disc is already rotating. Okay. And also a red line to represent the total angular momentum of the system. Okay, so the gold refers to the gold, the green refers to the green, and the red refers to the two disc system. Okay. Wait, what did you just say about the red?
Always the same.
Red is always the same. Guys, go ahead and draw that in your notes. What Logan just said. Right. So the red is always the same. The red never changes. Did you guys just draw that line for the two disc systems? Right? Because the angular momentum is always conserved. Always conserved. Okay. Angular momentum is always conserved. Okay. Now, guys, do you think that these two discs are going to have the same final angular velocity? Because they're going to be spinning together? But angular momentum, L, I know is I times omega. Right. Now, these two discs, when they're stuck together at the end, they do have the same omega. Right. Do they have the same I? No. The green one always has twice the inertia of the gold one. Maybe it's like twice as thick or twice as massive or something. Right. That can give twice the I. Okay. And then So, guys, when they're stuck together and they're rotating, which disk has more angular momentum? The green one, are you guys saying? Green one has more angular momentum, right? Wouldn't that be true? Right. In fact, the green one has what fraction of the total inertia? Guys, what's the total rotational inertia in the system? Like 3i? And doesn't the green have 2i compared to 3i?
Yeah.
Which would be 2/3?
Yes.
Right? And doesn't the gold one have what fraction of the total inertia? Yeah, 1/3 of the total. Right. So how's this gonna finish off? Because I'm still covering up part of the graph. I'm covering up what happens to the green curve and what happens to the gold curve. Go ahead, draw on your notes. How do you think it's gonna finish off? Now, there's some tiny interval of time where they're sticking together. Right? So there's a sort of a sudden change. Right? And then after they stick together, they're gonna both rotate together again with the same angular velocity. Okay. But this graph that you guys are drawing, it's not angular velocity, it's angular momentum. That's what L is. Okay. Again, that's a function of time. Okay. Okay. Here, I'm gonna take a trip around the room and see how many guys are. Yeah, okay, that was pretty good. Wait, is that? Did I put that in class? Ooh, no, it's not. It's not actually hanging for me. Wow, I didn't put this one up. I think so Nathaniel got it. So I was gonna figure out what this looks like. Yeah, Austin got it, Slot got it, yeah, Logan got it. Yeah, Jessica got it, Lily got it. Okay. Yeah. A bunch of guys are getting this. Awesome. Okay. So it's gonna finish off. It's gonna go like this. Right. Isn't that exactly what we walked through? Right. So this T drop is like at the point where it's like the gold is starting to land on the green disc, right? And there's a really tiny time interval where they start to stick together and this friction is taking over. Right? But there's a before they stick and there's an after they stick. Right? And that's the main parts of the graph. Okay. So before they stick, this green one wasn't rotating at all, had zero angular momentum. Right? And all the angular momentum was in the green disc. Right? Of course, the sum of these two curves is always this red curve, it's just a flat line. Right? Now, after they stick together, you guys remember you were saying that the fact that this green one has twice the rotational inertia compared to the gold, right? It should have twice the angular momentum because they have the same angular velocity. Okay, so here I'm still playing off this. Okay. They have the same omega. They have i's a ratio of 2 to 1. Therefore, the angular momentum should be 2 to 1, and that's exactly true. You see this green curve is twice as tall as the gold curve. That's it. Okay. Guys, what about this? What if these two? I can make this a little simpler. Guys, what if I did I and I? What if these two disks were identical to each other? And otherwise, same scenario. The green one's spinning, the gold one lands on it. Right? How would this graph be different? How would it end differently? Yeah, these would end the same, wouldn't they? Wouldn't they be the same? Like this green and gold would be just like halfway up the red. Guess that? Right. What about this? What if I reverse the disk? Like, what if I put the 2i up here and the single I down in the bottom? Right. Okay, so now the green one's the really light one and it's spinning, and I got this big, heavy gold disc kind of gonna land on it. What do you think would happen to the curves then?
Yeah.
Do you think they would probably cross? Like the gold one would be way up here and the green one would go way down here? You guys think? In fact, would it slow down? Hey guys, what if you do this? What if you do a 10-to-1 ratio? What if I I should write this down. What if I have a gold disc on top and a green disc on bottom? Right. The green disc is already rotating with some omega. Omega naught. And what if this is I? And what if this one's like 10i? 10i. Okay. And okay, this one starts out not rotating. And I'm gonna lower this until it lands on the rotating disc. Okay. If this was spinning at like 11 radians per second, and then I land this on it, it's gonna slow way down. Maybe like 1 radian per second or something pretty close to that. Right? Something like that. Okay. And then okay, so the angular momentum of this bottom disc is gonna greatly diminish. Like it might go from here all the way down to like way down here, wouldn't it? This green curve would go way down here. I think this gold curve would go like way up here, wouldn't it? Ah, all right. That. Ooh, let's do angular momentum of a point map. Guys, here's another question AP asks every year. Again, some version of this is what if I have this stick that's free to rotate about this X point? You guys see this X point right here, right? And I'm gonna take some blob of clay right here. I'm gonna throw this blob of clay. It's gonna stick to it right here, and they're gonna start rotating together. You guys see that? Right. Now, how fast do they end up rotating together? And this is really a momentum question, but it's also rotating. So something to do with angular momentum. Right. Now, guys, here's a really weird concept. You guys ready for a really weird concept? Right. This point mass, just moving in a straight line, has angular momentum. What? How's that? How's angular momentum? Right. Well, the angular momentum, we're talking about something rotating, but this is just a point mass moving in a straight line. So what's the connection? Right. Because when it's applying a force here, when it's colliding, it actually provides a torque about this point. Okay? So the angular momentum associated with the point mass is the regular momentum right here, mv, multiplied by this perpendicular radial arm, r. Yes, yes. So r cross mv. Right? Now, guys, in the past, guys, I'm telling you how to pass the test. Guys, in the past, I've always seen AP ask a question where this is coming in strictly perpendicular. So this cross product just simplifies it. It's just mv times r, or rmv. Okay. Right. Now, if it's coming out in an angle, you have to consider like sine and cosine and all this. Right. But you just multiply rmv. Can you guys do that? Okay. Okay. So that's the angular momentum provided by the point mass. Okay. Now, angular momentum, you guys know, also has something to do with like I times omega. So if you figured out the sum total of the I, and I think the stick right here itself, guys, does this stick look something like this maybe? Right. Now, oftentimes AP, they want to give you questions, multiple choice that you can oftentimes answer within like a minute or two. Right. So they might just call it I and not even dig into this level of detail. They might just call it I of the stick. Okay. But this point mass right here has some I also, and that's your MR squared of a point mass. Actually, I do recommend memorizing this one at least, just for a point mass. Can you guys memorize MR squared? Yeah. Although I think it's on it should be on your formulas anyway. Well, they say I is sum of MR squared, so for a point mass, it's just MR squared. I like that. Right, so right, let's do a couple of puzzles related to this. All right, see if I can go some numbers that you got. All right, let's say let me turn this into a guys. I'm gonna turn the stick right here into a paddle wheel. Let's go paddle wheel. So call us paddle wheel. Paddle wheel. Okay. It's gonna rotate about its center. So there's the center axis. The axle, I'll call it. Okay. See, it's got these little paddle arms right here. Okay. Okay. And let's say I take a blob of clay. Okay. And it's got some mass. It's coming in at some velocity. V. Okay. It's gonna stick right here. It's gonna stick right here. Okay. This has some radius. Call that R. Okay. And this whole paddle wheel has some rotational inertia. I'll call I. They said, right. That's all in terms of variables. Guys, do you want to? Do you want numbers? Or do you want to solve this in terms of variables? What do you guys feel like? Numbers in here. Okay, yeah, we can do numbers. Okay. And so let's say the mass of this clay is like 1 kilogram. Okay. Which do I have a kilogram? Well, here. So like this much. What if I had this much clay? That's great. And I'm gonna throw this with a speed of like 20 meters per second. Okay. And let's say the rotational inertia of the paddle wheel is what was your you guys remember the big little pipe system I had the other day? We were getting somewhere between like 0.04 or 0.1 or somewhere like, or 0.2 maybe. Let's call it how about 0.5 kilogram meter squared. So we got that. Okay. And let's call this radius right here up to this paddle arm. This radius right here. How about 0.6 0.70 meters. So like 70 centimeters. And most of a meter stick, 2/3 of a meter stick. And question I have is after this clay collides with that paddle wheel right there, how fast is this going to start rotating? So what is the post collision angular velocity? Call that omega, of course. Right. So after this clay collides with this paddle wheel, it's going to stick to it. It's going to stick to it. Right. This whole paddle wheel is going to rotate about this axle. How fast? Okay. All right. All right, you guys got all that?
That's it.
Okay. Now, you guys know what inspired this question is we were just going over this one right here. So what do you guys think is a good first step to do? Good first step.
I said L equals R cross MB.
Yeah, I'm looking at exactly. Yeah, I'm gonna do what Nathaniel said. You guys see this gold box right here? Let's start with that. Figure out how much momentum is in the system. Oh, I should have said specify the paddle wheel starts at rest. I mean, it would probably say that, right? Paddle wheel starts at rest. There's no friction with the axle. Okay, so common simplifications. Okay, yeah, let's do the angular momentum in the system. It's all coming from the fact this clay is being thrown in a straight line. And so that could be R cross MV or just RNV or NVR because it is coming in perpendicular to the wheel or wheel arm. So I call this radius size here 70 centimeters or 0.70 meters. Let's take the base SI units, that many meters. The mass of the clay, we're calling 1 kilogram. And say I threw this at 20 meters per second. A pretty good clip. I think it's about 45, 50 miles an hour or somewhere in there. 0.7 times 20 per decibel. Okay. So this is telling me 14 units of angular momentum. And guys, can you guys see the unit for angular momentum? Kilogram meter squared over second. Kilogram meter squared over seconds. Right. There's an alternate unit. I think it goes meter seconds. I think if I remember right. Okay. But that's the angular momentum of the whole system, and all coming from that blob of clay. But of course, it's conserved. Okay. And so you guys know how much angular momentum is in the system? Okay. But that wasn't exactly the question, guys. The question is how fast is the paddle wheel spinning as a result. You guys see that? Okay. So this is part one. Okay. But we got more work to do. What do you guys think is a good next step of the puzzle? Okay. What's another formula you guys know for angular momentum? Okay, it's not R and D because we're done with that. What's another formula? Yeah, I omega, right? I omega, right? Something like that. Okay. Now here's where we got to be careful because it depends what level of detail we go to. Now I'm having this clay stick to this paddle arm wheel. It's going to stick to it. You guys, if it sticks to it, do I have to consider both the rotational inertia of the wheel, which I gave you right here, but also this point mass worth of clay that's stuck to it? Because they are rotating together, aren't they? Right. So the angular momentum of the whole system is actually equal to the eye of the wheel plus the eye of the clay, all stuck together. And then they're rotating together, and we're going to figure out how fast. You like that? Right. Let you guys digest up to that point. Okay.
Which we can find by.
Is there any questions so far?
This?
Anything I've written? And here, we're going to do one more substitution in terms of variables. System equals, okay, so I wheel, which I gave to you. Okay, guys, here's the I of the wheel, and AP will oftentimes just tell you that value for this type of scenario. Okay, right. But guys, for the clay, what should I substitute in for the clay? Exactly, mr squared, because we're going to treat this as a point mass, and it is at distance r from that axle of rotation. Yeah, right, it has some mass in, okay. And then omega right here. Okay, our ultimate goal is to solve for this omega. Okay, but I think we can start popping in numbers at this point. Guys, what number am I going to plug in for the angular momentum of the system? Exactly. That's what we did all this work for.
Yeah.
This RMV is 14 kilogram meter squared second. 14 kilogram meter squared per second. It's like 14 units. Is equal to, now the eye of the wheel, I said, let's call that 0.5 kilogram meter squared. 0.5 kilogram meters squared. Okay. To make it heftier than that pipe system we had the other day, but kind of comparable. Okay. And then the point mass of clay. Well, it's got 1 kilogram worth of mass, and it's colliding at 0.7 meters, and that's being squared. Okay. Oh, guys, what's 0.7 times 0.7? 0.49. Okay. Which interestingly is, I didn't plan for this. I'm just making up numbers on the fly. That's actually really, really, really close to the angular, rotational inertia of the wheel itself, isn't it? Okay. So it's kind of like we sort of doubled the rotational inertia of the system. Okay. And then omega, we're solving for. Right, calculator time. Okay. Actually, oh, guys, everything in parentheses. This is very, very, very close to 1. You guys think this answer is going to be very close to 14 radians per second? Yeah, that's 14 over 0.5 plus 0.5. That's great. Look at that. Yeah, there we go. Omega final equals 14.14 something. Radians per second is what that would be. 14 radians per second. Guys, isn't 2 pi radians 1 complete trip around a circle? Is that about 6.28? If you double 6.28, is that fairly close to 14? Right. What I'm trying to get at is approximately how many rotations is this making every second? 2. Yeah. Guys see that? All right. You guys saw that? All right. Let's do another one. All right. How about this? Let's do one that's fairly similar to that. Suppose I break out this turntable and give this a spin. I'm going to take this 0.5 kilogram mass and just drop it right there. Okay. Oh, do you guys see that slow down a lot? Slow down a lot? Okay. Now, if there was truly no friction, then maybe this should just keep going all day. Okay. But I wonder if it was spinning so fast and you drop this mass, pow, right there, if you could predict. You guys saw it spins more slowly after I dropped it. Okay. Kind of like here's the linear equivalent to last semester. You guys remember last semester? It's like if you're pushing your grocery cart, okay, and then you start throwing in groceries as you're going along the aisle. Isn't that increasing the mass of your basket? Okay. Okay. Well, here's the rotational version of that. I'm like increasing the rotational inertia of this turntable by dropping this mass on it at some location. Now, if I drop it right in the center, it probably doesn't change it very much at all. Okay. But if I drop it near the edge, that's a lot more inertia, and it slows it way down. Ooh, is it? And so let's do a calculation here based on what I just showed you. Let's say got this turntable. Okay. I'm gonna drop this 0.5 kilogram mass. So 0.5 kg, right here. Let's try to model pretty much exactly what I just did. Okay, so okay, let's say I dropped it at like a 10 centimeters out. So I'll call this distance from here to here. I'll call that little r. Let's say that's 0.10 meters. Okay. Now I do need to figure out what's the rotational inertia of this disc. Okay, let's see if we can do that too. Here, guys, what do you think is more massive? This 0.5 kilogram or the top surface of like this plank of wood I'm turning? I think this feels a little more massive, and I don't actually feel this, but I'm gonna kind of guess. Maybe this is about 0.2 kilograms. I'm just guessing. Maybe 0.2 kilograms worth of mass. Okay, and this has it's an octagon, but it's fairly close to a circle. This has a radius of about 15, 16 centimeters. Let's call it 15 centimeters. Okay. And if you put it all together, what I'm trying to work towards at this moment is this right here. Isn't this basically the shape of the turntable? Okay. So let's pop this all in right here. So 1/2 times a mass of, let's call it 0.2 kilograms, times a radius of 0.15 meters being squared. Okay. That gives it this rotational inertia. You guys see that? 0.00225. You guys see that? Okay. Now, really, it's just a back of envelope calculation. I'm really just making some estimates. So let's call this I of the table, turntable. I'm going to round a little bit. Let's call it 0.002. That's kilogram meter squared. Okay. Now let's say I was rotating this with an initial angular velocity of, how about 1 radian per second? Just to make something up. Okay. So after this mass collides with the turntable, it lands on it. Okay. And notice it doesn't matter how high I dropped it from or how fast it was landing. All it matters is that it's like math, just proof, just like it just appeared on it. Okay. Just from that fact alone, this whole system's going to slow down. Okay. Okay. And we can go through conservation of angular momentum to figure this out. So if this was my free response question on the AP exam, the very first thing I would write is this: sum of angular momentum before equals sum of angular momentum after. Okay. Which looks like that ice skater poster. You guys remember the ice skater poster? Okay. That's what that says. And so, what should I write next? What goes right here? Yeah, I omega naught. Okay. Okay. And then post collision,
I omega.
I got well, this is I of the table, the T for table. Okay. Okay. Plus, ooh, guys, this half kilogram mass landing pow right there.
Oh yeah.
Isn't that like mr squared? Right. And then I got omega final right here. Initial final. You can solve for that. Okay. Let's throw some numbers. I think we got just enough time to throw some numbers in and get an answer. Okay. So for I of the table, I was calling that 0.002 kilogram meter squared. Okay. I was saying let's rotate that at 1 radian per second. And then I got 0.002 kilogram meter squared here, plus a half a kilogram times 0.1 meters being squared, then omega final. We're going to solve for. Okay. All right, so I'll fill this in my calculator and think I can beat the bell on this. 0.002 times 1. Okay. Divided by, and then in parentheses, 0.002 plus 0.5 times 0.1 squared. Okay. I'm getting, here, I'll write this out here. Omega final equals 0.29 radians per second. Okay. Guys, is that somewhere between a quarter and a third of the original rotation rate? Because the original omega was 1 radian per second. Now it's somewhere between a quarter and a third of that. That looks fairly similar to what you guys should solve. Didn't it slow down by maybe a factor of 3 or so? Yeah, it's pretty close. All right. Okay. You guys made good progress. Yeah.